Hello, everybody, and welcome to my talk. I want to add a little bit of the talk that Sean has given to us. You should totally look into WoW. It's totally worth it. And also, I'm not as proficient in giving talks like Sean is. I'm more of the speakers that put heaps of information on you, and you have to do it away in the upcoming weeks. So let's talk about modules and how the situation is right now using modules, and not only on one platform like it has been in the past couple of years, but also on additional compilers and platforms. There's a lot of information here. I'm only scratching the surface. What's the topics that I've been putting here on the slide is worth probably 4 to 5 hours, and you have only one, so I feel sorry for you. And to the end, I will give you a short demo about things work today, and this is hopefully within the advertised time. If not, you won't have a lunch, but probably an early dinner. Okay. I'm an electrical engineer, so my point of view on C++ is completely different to most of you probably. And I'm in the business for a long time, so I had lots of opportunities to make my faults, and I took many of these opportunities. I'm also a member of the committee for a little bit more of 3 years now, mostly in evolution and also in the tooling study group 15. So, please a quick show of hands. Who heard about modules before? Besides the title, of course. Okay, this is good. Who knows a little bit about modules, at least? Okay. Who has actually done something with modules? Yeah, you should raise your hand as well. And lastly, who is actually using it in production? Oh, this is the expected result. So what I will give you in the hopefully 10 minutes now, the shortest introduction into modules ever. Let's see how if I can get it in 10 minutes. Okay. What we usually do in our development, we have libraries and we have library consumers, and the library usually looks like this. We have implementation units, we have library interfaces in form of headers, and our translation units from the consumer side are like with any translation unit that we compile in our C++ world, independently compiled. So we have a barrier between the library implementation units and the consumers of the library. There is no barrier that is between the library interface and the consumer. And this is a problem because of the textual inclusion of the interface headers, we have no longer control about what actually the interface of our libraries mean. You don't start with a given context and state of the compiler, but you need to take into account that something before the actual inclusion of our library headers happens within the compilation of our C++ code. So what the compiler actually does is during the compilation, it starts out with no declarations, it may have some predefined macros and macros from the command line, and the compiler state also includes a couple of compiler flags that, for example, define the class layout. During the compilation, the compiler will collect all the information that it gets from the source code, like declarations, definitions, or the language entities. And at the end, all of that is discarded. The only thing that remains is the object file from the compilation. With modules, things are a little bit different. We want to make sure that our interfaces are actually dependable and reliable, and we know what we mean with our syntax. So to do that, the interface is no longer a header file that is textually included, but it becomes a translation unit on its own. And this means that the isolation barrier between the architect of the library and the consumer of the library is now in between these compilation units. And this poses a problem because now we can give information about the language entities in the interface to our own implementation and also not to the consumer. So we need to find a way to get around this. And this new communication channel is called BMI, and this is a short for Build Module Interface. We have actually not only one interface in the BMI, this is actually a two-phased interface. One is looking into the module itself. This is what you see on the right. And there's also an interface to the consumers of a module. And you, as the library architect, decide which parts of the entities in your translation unit that contains the interface is visible to the consumers. And this is done by this export keyword here. So you are no longer forced by the language requirements, what you put into your translation unit with the interface. Now you can put what you want and only make the parts that you actually want to make the interface known to the importers of your module. On the compiler side, this means you're no longer throwing away all the definition and declarations that have collected during the compilation of the module interface, but now everything in there gets written to the build module interface. This is a second artifact that the compiler will create. In addition to that, as far as I know, all implementations also put some information about the compiler state at the beginning of the compilation also into this BMI file, so that the compiler can then decide if an importer of a module can use this particular compilation artifact and make sure that these match up together. Okay, let's look at a very small module just to introduce some vocabulary. We have module interface units. There's only one in every module. And we have module implementation units. You can have none, or you can have as many as you want. These translation units carry a name in their module declaration, and this is why we call these translation units and these modules named modules. Then all the pieces throughout all of these translation units that comprise a module that start with the module declaration up to the end of the translation unit, all of these pieces form what's called the module purview. All language entities that appear within these pieces of the translation units belong to that particular module. This is different to what we have been used to the past 30 or more years. Everything that we have been programming in the past was actually part of a module, as we now know, and this is the global module. The global module contains all the existing code as we have been using it. Every translation unit of a module can optionally have also a part of this global module, and this is called the global module fragment, where we place all this stuff in here that we have from the past and want to use in the implementation of our module. And then such a global module is just a declaration without a name, because the global module doesn't carry a name. So with this, we can look at the first thing that you need to understand about modules. As I've said before, you export things that you want to make available to the consumers of your library, but this exportedness only applies to the name of the entities that you want to make available. Many people think that's the whole declaration of a language entity that is exported. No, it's just the name. Exportedness is about visibility of names and name lookup. So in the syntax, we see module declaration without a name. So this is the global module fragment. And here, following the first half, is the actual module declaration with the name of the module. And in the beginning of this declaration, we have an export keyword. So this makes this particular translation unit the module interface unit. It's only the interface units where you can export things from. What you can export is not only entities, but also you can import other modules into your own module. And if you export it from there, now you incorporate the whole interface of this other module into your own. And you can still use traditional textual inclusion. But as I said before, this is part of the module purview. Now this header file that is included here is also part of the module purview. You can no longer use this header somewhere else outside of the module. Please keep this in mind. The entity is part of the module, and if you reuse the same thing, you're talking about different entities. And here's an example of an exported function declaration. So you put the export keyword here, and what's exported is actually just the name of it. Everything else is not exported, but these semantic properties become reachable. So you have a separation between reachability and visibility. I will not expand on that. I have given a talk in 2021. If you want to learn more about it, watch this talk. And in the implementation unit, we have a similar module declaration, just without the export keyword in front of it. Then the next thing you need to know about modules, entities which are in the module purview belong to a module. So in the past, you know probably what an external linkage means, so you can relate to entities in different translation units throughout the whole program. But now with modules, if you declare an entity within the purview of a module but don't export it, it gets now module linkage. This is a new kind of linkage very similar to external linkage, but it applies only throughout the whole module purview. Things that are in the module purview only can be referred to from within the module purview. And this gives us name isolation. Here we see two modules, and both of them have a function foo at namespace level, which is not exported. Even though the name is the same, the semantic properties are the same, these are different foos. So you can take this to your advantage and don't have to do crazy things to avoid clashing the names in the linker, for example. So if you import both of these modules into your code, you can do that safely, because even though you use the exported functions bar and bus here, and which in turn call into the functions foo, each one of them can do that without giving problems at a linker level. These are different foos. And with modules also comes the notion of attachment. Everything that is in the module purview belongs to the module, and this is said to be attached to a module. So instead of saying just foo, you say foo at, that is a part of the module. Here we have foo at module 1 and also foo at module 2. And this is the third kind of thing. Because of this attachment, you get different linker symbols, and this is how it's typically implemented in the compilers. the last part of this introduction is we don't only have primary module interface units, we also have module implementation units, as seen before, and 3 more different additional translation units for named modules, interface partitions, internal partitions, and the third one is not actually a translation unit, but it's you can consider them, consider private module fragments just like a module implementation unit. All of these belong to named modules. All of these provide parts of the module purview. None of these export macros. This is an important thing. Named modules never export any macros. And all of these are fully isolated. And by that, I mean, you can't influence the semantic meaning of a module from macros that are part of your importing translation unit. And also, because no macros escape the module, your importing translation unit is not affected by macros within a module. And this is full isolation. In contrary to that, we also have things called header units, which is just a header compiled up to compilation stage 7, and then will emit a BMI like the other module translation units do. But the difference is header units belong to the global module. Header units export macros, and you can't architect it. Everything that has external linkage becomes part of the interface of a header unit. There's no way around it. And even though many people think header units are the easy way to transition into the world of modules, these are actually the worst. It imposes so many problems to build systems. Avoid them if you can. You should really know when to use header units. So the first segment of my talk is over. Let's go into advertisement. Yeah, just kidding. Let's talk about compilers. The next slides will show you what the implementers of compilers say about their module implementation, how we document it, and what the compilers themselves advertise to your programs. Currently, as far as I know, there are 3 compilers that actually implement C++ 20 modules. This is GCC and the libstd C++ standard library that comes with it. It's clang and it's also MSBC. I had the same slide, not exactly the same, but a similar slide 2 years ago in my talk. Now, if you probably have seen this talk, there's much more green on this slide here. So GCC and Clang had made huge progress in the implementation of modules. Even though bread and butter pieces like named modules and module partitions are still in a partial implementation, things are missing, and in particular, name lookup is still a problem with them. Please be aware of that. I like to see that all implementations now have converged on the strong ownership model. This is ownership is the kind of thing. If you have a name attached to a module, what does it mean to symbols? Now all implementations do the same here, and this is a good thing for you and us as a community. And lastly, what about the modularized standard library as is it defined in the C++ 23 version of the standard? MSVC actually ships a modularized standard library. libc++ is in an experimental, let's call it more like a proof of concept stage of doing that. And libs.c++, as far as I know, didn't even try to provide a modularized standard library. And this is that. I've been alluding to that here earlier. As far as I know, GCC doesn't provide any means to make sure that your BMIs that you've compiled are actually usable from the importers of a module, but Clang and MSVC do. MSVC is a little bit more lenient. It will give you warnings. You can ignore them, but then you should really know what you do. Clang, on the other hand, is really strict on that. Unfortunately, it doesn't tell us which compiler flags are required to match up between the importers and the module architects. And it's kind of funny. It gives you warnings if these things don't match up, and you can actually suppress this warning, but it will refuse to import your module anyway. Then this is kind of a hot topic. What about file extensions related to modules? Some people have strong opinions on that. Some people say modules are broken because of that. You can't use them. No, this is not possible. But in my opinion, who cares about extensions? The build system has to take care. And actually, all implementations support any file extension that you like. And this applies both to named module translation units and header units. They are pretty similar here. But all of them have a preference. This is important for you if you want to compile modules manually from the command line. If you're using MSVC and GCC, you can build a full program out of modules and importers of modules on a single command line if you use the correct extensions. With Clang, it's totally useless to use the preferred extension because you can't compile it with one single invocation of the compiler anyways. So now we have the technicalities of these implementations and modules out of the way. Let's talk about, you're new to modules and want to modularize an existing code of yours. How to do that? In the demo code that I will be presenting later on, there's the smallest module that I've been using here is an external library called ArcPath. You may have heard of it. It's a C++17 single header file only library that is totally portable. And this is something that you might want to use in your programs as well as this is a command line parser. It's very simple. There's just one namespace, a couple of things that are not meant to be used by the users of the library. As usual, just giving a namespace detail or something like that. And then just a few items, just a few language entities, 2 classes that are actually meant to be the interface. So, if you're new to modules, have learned everything that I've told you up to now, blue-eyed, bushy-tailed, really determined to make this into a module, what you probably may do, you slap an export, module export declaration here, and export all the things that are meant to be the interface, right? Sounds simple. It actually is simple. And let's compile it. In alphabetical order. Here are the compiler options that you have to give with Clang. And yeah, it doesn't compile. It says something about global module, struct iterator traits. None of this appears in our module. What's going on? Okay, GCC has a better implementation, let's try it. And it fails just the same. Also with iterator traits and some other stuff. And lastly, MSVC. Whoa, it compiles. What's going on here? Yeah, but it gives us a warning. Include algorithms in the purview of module argpath appears erroneous. What did I forget? Anybody? Yeah. This is an option to import the standard library as a module. But MSVC is helping us here consider moving the directive before the module declaration. And the other option you have, or replace the textual inclusion with import algorithm. In other words, use a header unit. But please don't use header unit if you don't need to. So we use this first option and introduce a global module fragment. Because, as I've told you before, the global module fragment is the part of your translation unit where you have to put all the existing header files into. And this is what we do. And when I mean all existing headers, I mean really all of them without exception. Don't put them into the module purview after the module declaration. So if we do that, let's compile it again. And the result is, yeah, we did the right thing, but GCC is like a bug. If you stare at it too long, it will fall dead on its back. Yeah, so GCC is now out of the picture in the rest of the talk. But I told you before, module interface units have two interfaces, one looking inside and one looking outside. The inside part is exercised during the compilation of the module, but you need to do unit testing or something like that for the external facing part. Here I didn't show you a full unit test suite for this argpath library, just a small piece of code to exercise some of the classes and functions in here. And let's see how this test goes. Clang again. Now it needs a different set of compiler options to tell the compiler where the BMI of the argpath module is. And now it starts to fail again. It's telling us something about standard string or something like that is missing. And with MSVC, just the same, also with standard string. The problem is there is a small part in the standard that says that the GMF is treated differently than the actual module purview. Only the end language entities that live in the module purview belong to that module. And this is the reason why only them are exported or incorporated into the BMI completely. To not blow up your BMIs and to not cause problems, the entities that are in the global module fragment and belong to the global module are only incorporated into the BMI to the extent that the compiler actually can prove that it is required there. And if you know, with templates, you can do crazy kind of stuff, so the compiler can't prove what you actually need. And so, in other words, you, as the user of a module, need to provide the missing pieces. And as Guy was correctly pointing out, imports to this solution, or others. So let's test it again. Clang requires to include the any header, and both compilers require this inclusion of the string header. Who would guess that from the module? I think this is quite user hostile. But no, we can compile the test source. But I didn't tell you the whole picture right now. There are still more things to consider. The library is using unqualified named lookup, and unqualified named lookup means you invoke ADL, and invoke ADL at least reduces compiler throughput. And it can lead to lookup failures, because not everything is made visible to the user of the module. So if you're instantiating templates, there may be entities in there that are not made visible to the user of this module, and it can lead to lookup failures. So as a general rule, try to avoid ADL wherever you can, unless you really need it. This is made for customization points, not for daily use. And the other thing is translation unit local entities that have internal linkage. If you expose them through other exported things like a class template or function template, you're exposing these translation unit local entities, and this means, and the standard says in no uncertain ways, an exposure makes your program ill-formed. And in all other cases, it's at least deprecated. So be aware of translation unit local entities, even if you're not using modules. I use ASIO. I will not go into that. This is way too much, but it's in the slides and also in the code that you can find on GitHub here. It has a technique in here that can be used to modularize existing libraries in a much more powerful way than just changing the sources like we did before. You have a proper global module fragment, you have the exports in the module purview just by importing, including all of your interface headers, and you put all the implementation translation units of your existing library into the private module fragment. So now you're using just one translation unit for the module interface and include everything in here. So it's more like a unity build of your library. And this makes it possible that you don't have to change anything besides translation unit local entities and unqualified lookup to make it into a module. Next, let's talk about build systems. As far as I know, in alphabetical order, we have build 2. I'm not sure how it's going on there. There's a little bit silence on the documentation here. But now we have CMake, and CMake now claims support for named modules, and unfortunately only named modules because header units are not yet supported so far. It technically supports clang, MSVC, and GCC if you like to compile your GCC with a patch supplied by Kitware yourself, then it would support GCC as well. Did I mention GCC? Oh, okay. And it not only supports, but actually requires module dependency scanning. Don't despair, this is a good thing. We have Evoke. Forget about it, probably it's dead now. There is MSBuild. MSBuild is what comes with your Microsoft toolsets and also with Visual Studio. And it ticks all the marks that you want to see. In particular, it's well documented. Then we have a newcomer, that is CMake. It touts a nicer syntax than CMake. It's based on Lua. It claims to support all of C++ modules, and it claims also to support all compilers. But their documentation is so weak, I can't even determine if they have module dependency scanning. And for some die-hard developers, there's also Make. I wouldn't recommend it. You need to do everything by yourself and everything manually. Okay, let's talk about CMake. This experimental support needs to opt into experimental API. Oh, sorry. What's going on here? Yeah, an experimental API, and you need to do this magical incantation to enable you the experimental new kind of things. One of these is how you tell CMake about the translation units that it needs to compile to make it a module. In the target sources, you tell, as usual, all the non-modular translation units like before, and all the other translation units from modules that consume BMIs, and these are the module implementation translation units. And then you have to differentiate between the translation units that form named modules. You place the module interface translation units here, and also the internal partitions, and all the header units get a different section. This is just syntactically accepted right now. It doesn't do anything. Let's hope for the future. And the second piece that you need to use with CMake, and this is also kind of an optional part, even though it's required. If you don't do it, you don't get a module out of CMake. And this is dependency scanning. So CMake requires that the implementation provides dependency scanners, and these dependency scanners report their dependencies in a standard blessed way. And out of these reports, it will create what CMake calls module maps, but please don't confuse them with the module maps from Clang modules. And it needs a build node processor that is actually capable of understanding all of this, in particular dependency re-evaluation. And there are two of them right now. This is Ninja and MSBuild. So in fact, this is not just one magical incantation, it's three of them. Just copy them into your CMake. And if you feel scared a bit at this moment, I hope you're not as scared as the audiences in the movie theaters 100 years ago have been. And Nosferatu was really scaring the heck out of the early moviegoers back then. So don't be a Nosferatu. Let's talk a little bit more about module dependencies. And here take, for example, another module that I'm going to use. And this is the probably well-known SDL library. To make it a module, I had to go with a composite interface that contains the primary module interface unit that imports and re-exports 3 module interface partitions, and one of them imports the other one to implement the interface. It's a little bit complicated because the SDL library is a C library, and much of the things that it makes available as an interface is implemented as not modules, but macros. And we can't export macros from a named module. So I had to use X macros to get rid of all the macros and make it proper language entities that I can export them. And as you can see here, we have a composite module, and this asks for dependency scanning. So, this is expandable here. If we supply, for example, one of these interface partitions to the module dependency scanner, the translation unit of it, maybe this one here, then the dependency scanner will come back with a report that looks like this one here. And this is the one that is blessed by the tooling study group in the in the C++ committee. And it says it provides the partition global macros of the SDL module that happens to be an interface. And the source of the translation unit is here. And to compile it, it requires another module. In this case, it's the partition with macros of the SDL module. This is the output from Clang. This is the output from MSVC. It's just the same at the parts that I've been showing you. It has some additional information that is not required for module dependency scanning. But besides that, these dependency reports are compatible between the implementations. And what CMake does then out of these reports is, as I said before, these module maps, and this is just a fragment of the compiler invocation, the required compiler flags to compile it, telling where to put the BMI and telling where the BMIs are that this particular translation unit depends on. This is with Clang, and the same is with MSVC. So what these module maps are by C++ are just parts of your compiler command line. Okay. These are all the technicalities. I hope you know everything about modules now and the ecosystem. Let's try to actually compile a program that consists only of modules. I don't know who has been here last year and seen my talk, but this is an expansion on top of that. During last year I've been developing it further. It was what you've seen at CPPCon and also at Meeting C++. And the version I'm using here is a slightly modified version of the Meeting C++ code that I've been presenting last year on a completely different topic. If you don't know what the program does, it's a client-server application. Both parts are just in the same program now. That will show short movies out of GIF files. And this application consists only of modules, at least it did last year. It uses the modularized standard library. It uses the ACU module that I've been showing before. It uses 7 more modules from within the application itself. And so the module structure after the discovery looks like this. The demo code has 8 named modules, 1 header that has been a header unit last year, but CMake doesn't support header units. So I had to demote the header unit into just a header file. It has as dependencies 4 named modules from external libraries. And it uses the modularized C++23 standard library. And this requires compiling your existing standard headers as they have been delivered with the Linux distribution, for example, or the Microsoft Visual Studio. You have to compile it for yourself because BMIs have to match. So you need to compile them for yourself. I'm pretty sure all implementations will require that you compile the modularized standard library out of the existing header files from your library. In addition to that, I had to add a little bit polyfill that are the missing pieces that are not yet implemented in the standard libraries of both libstd C++ and the Microsoft SDL implementation. And this is the generator gladly given to us by Casey Carter from the Microsoft team. It has a very good implementation of generators, and it's fully and complete implementation of that. I am supplying a partial implementation of std print and also std start lifetime as. This is actually library functions that are required in the demo code. The reason why, watch my keynotes from last year. And with that, let's try to compile it. Okay. Let's start with MSVC. Last year, I've been showing that MSVC can compile this code. But last year, I've been using MSBuild, and this year, I'm using CMake. The projects are already configured. It takes a long time because of SDL. So we are just invoking Ninja to actually compile the stuff. And if you look carefully, you see scanning steps and build steps. And what's going on here in the scanning steps is this incremental discovery of the whole network of modules that are being used here in this demo code. And as expected, it compiles. Let's move on to Clang with the same source code, which, by the way, is completely portable. Exactly the same command line. What's going on? Last night it did. Why doesn't it compile today? Yeah, I'm such a jerk. Oops. Clang has a problem. And this is the stuff that I've been alluding to. The implementation of Clang is not complete yet. You will sooner or later run into problems, parts that have not yet been implemented. But this is actually not wrong anymore. 2 weeks ago, I've been at the Varna meeting of the Standards Committee. I had a chance to talk to the implementer of Clang modules. And we had each morning breakfast and were talking about all the problems that I had in preparation of this talk. And this particular problem is solved now. There are also some more problems that are already solved as well. And hopefully we'll land in LLVM 17. The cutoff of LLVM 17 is in 4 weeks from now, so maybe you should use LLVM 17 instead of 16. But this is only the easy part here. If you fix this problem, and you can totally fix it, you run into the next problem, and afterwards the next problem, and the next problem. It took me literally a month to get and find fixes for all the problems that Clang has in its current implementation. And ODR violation that is pointing out within libstud C++, yeah, there are ODR violations in there. and also the platform I'm using here. This is msvc2, a POSIX system on top of the Windows kernel. And this is the only distribution that actually comes with Clang 16. And so we need to apply a ton of fixes that you can find on my GitHub and try to compile it there. You did it. So with pure dedication, you can actually achieve things with Clang 16. And now let's see if it actually runs. Compiling is one thing, running is another one. By the way, this is a single-threaded application that totally relies on asynchronous execution framework, coroutines, and all this good stuff. So what's my, oh, can I find it? I need to put on my glasses. So my conclusion about all of this that I've been showing so far, if there is one thing that you want to use with modules, and if it's only this one here, I totally recommend to use the standard library as a module. This is how it would look like, you know, on dependencies and how you can implement it. But it's totally worth it. This is measurements that I did last year. At the time, then the MSVC implementation of the modularized standard library was technically complete, but had too many bugs to be actually usable in production. This is why I came up with my own implementation of a modularized standard library, and this is what you'll see if you compare these three different options you have. If you want to provide the complete API of C++ as it's defined in the standard, for example, you place all of these standard STL headers into just, for example, all-state HPP, and you include it into a program or a translation unit that does nothing like here, and you measure how long it takes to provide all the API. On my machine back then, it took me roughly 2 seconds or so. Not doing anything with the API, just in making it available. And with my implementation of a modularized standard library, it's not longer taking 2 seconds, but just 15 milliseconds. And if I would go with the implementation by Microsoft, who does it properly, it's unmeasurable. Named modules are really, really fast in providing APIs to your libraries. If you possibly can, go with named modules. And this matches up with the measurements that I made 2.5 years ago in my talk in 2021, where I was presenting my findings in modularizing the formatting library. And the formatting library has many more possibilities how you can use it. And with most people probably use it as a header-only library. And if you want to provide the full API of the formatting library, it would take just a little bit more than 1.5 seconds just to provide the API. You can use header units, then they're down to a little bit over 100 milliseconds. But if you go with a full named module, as you should do, then again, it costs you nothing to provide the API. So if you would take into account everything that I've been showing so far to you, all the problems that some implementations still have, thinking about, dependencies, all this, but also take into account the benefits that you can get out of modules, I would say yes. You probably want to at least take a tour into modules and figure out if it's something that you want to do. And at least I use it in production, and I can say, yes, it's actually worth it. We got compile times down from 20 minutes to 1 minute. So this is my advice. And here are some resources. For example, the most important milestones in the development of modules from 2004 by David van de Voorde was explaining how you could possibly do modules. And in 2018, the technical specification of the modules was finished, and Microsoft was actually building the Edge browser on top of that, as far as I know. And the links to my GitHub repository, where all of this code that I've been compiling here is, and also the slides of this talk are also on this GitHub repository. And you can find all the changes that I had to do to make this happen. And probably study it and think about what you need to learn from it and what you can use in your own efforts to modularize existing libraries and what to watch out for. And with that, I'm done. And I'm ready to take questions.